Hello students, welcome to the channel. Today concept is current electricity, third lesson, 12th standard. In this one we discuss effect of temperature on resistance and resistivity, related problems. So that we discuss. See here, what is the lesson name now? Current electricity. Current electricity, it is a third lesson in 12th standard. See, in this one we discuss effect of temperature on resistance and resistivity. This is the concept. First we discuss what is resistance and resistivity. See here, resistance now, resistance means it is the property of material. So means we can write it as electrical resistance. Electrical resistance. So electrical resistance means it is the property of material which obstructs the flow of electric current by conductor, or which obstructs the flow of electrons. Flow of electron means which opposes the flow of electrons. So that we call, that property we call it as electrical resistance. It is the property of material which obstructs the flow of electric current by conductor. So that is called as electrical resistance. It is represented by letter R. It is represented by letter R. So R equal to what now here? See, volt per ampere. So means potential difference per current. So that unit is volt per ampere. We can write it. So volt per ampere, it we can write ohm, we can write. So what is the unit of resistance now? Ohm. See, what is the formula for resistance now? We can write it as R equal to rho L by A. Here rho means resistivity, here L means length of the conductor, A means area of conductor. See here, resistance now, it is the obstruction offered in the flow of electrons or flow of current by conductor. We call it as resistance. So this resistance is depends upon what now here? Length of the conductor. Length of conductor, length change na, its resistance change. And once A na here, area of conductor. Area of conductor. See, and now material, material change, its resistance is change. And now temperature change, now its resistance also change. That is the main concept. See here, effect of temperature on resistance and resistivity, how it will change, either increasing or decreasing or constant, that we discuss. Yes na? Resistance means it is the obstruction offered in flow of electrons or flow of current by conductor. We call it as resistance. Resistance na potential by current. So potential na volt, current na ampere. So volt per ampere we call it as ohm. See here, we can write it as R equal to rho L by A. Rho means here resistivity. Resistivity, it is also property of material which obstructs the flow of electrons or flow of current by conductor. See, resistivity, L na length of the conductor, A na area of conductor. Means this resistance is depends upon length of conductor, area of conductor, material and temperature. So it will change na, it also changes. So see, area increases, resistance decreases. Why? Because denominator na area increases, resistance decreases. Length increase na, resistance also increases. So material change na, resistance change. Temperature change na, resistance change. It is increases or decreases. That will be we discuss by one. Conductors how it will change, insulators how it will change, semiconductors how it will change, that we discuss. See here, here rho is there. So before that R we can write it as, so what na, volt by, so means voltage. by current na, current we can write. See here, before we derive, so current equal to what na, here I equal to v e n a, means v means here, vd means here drift velocity, e means charge on electron, n means number density, means number of free electrons per unit volume, a means area of cross section. See here, instead of vd we can write ev by ml tau average. It is the formula for drift velocity. So we can write here I equal to, so ev by ml tau average into ena. So from that what we can write now, ne square tau av by ml we can write. See here, I changes to this side, remaining changes this side. Now what we get now here, ml by ne square tau a, that equal to v by I. So means v by I what we can write now here, so means voltage now v, current now I. So v by I now, instead of v by I we can write this value. So we can write r equal to ml by ne square tau a. Here see, what is actually resistance equal to what na formula, rho L by A. Before we can write here, see, resistance equal to what, rho L by A. Instead of rho here, see, this value is there, so this we call it as rho. So means resistivity. So what is the formula for resistivity now? See here, m by ne square tau average. It is the formula for resistivity. It is the formula for resistance. Yes na. So resistivity means m by ne square tau average. Resistance na ml by ne square tau average a. Yes na. See here. So this one I write na here. So resistance. What na here? Resistance formula I write here. What is the resistance na? M by ne square tau average L by A. It is the formula for resistance. What is the rho na? Rho equal to m by ne square tau average. See here in this one, so m equal to mass of electron. Here see, n means number of free charges, means free electrons per unit volume, per unit volume. See here, e means charge on electron, charge on electron. Tau average means average relaxation time, average relaxation time. So L means length of the conductor, length of conductor along which current flows, current flows. Yes na. See, A means area of cross section, area of cross section which is perpendicular to flow of current, flow of current. This is the each term. See here, m na mass of electron, n means number of free charges per unit volume, e means charge on electron, tau average means average relaxation time, L means length of the conductor along which current flow, A means area of cross section which is perpendicular to flow of current. So each term, this one. So resistance means m by ne square tau average into L by A. Resistivity na m by ne square tau average. So by using this we can discuss how temperature change, resistance and resistivity changes. Yes na. See for example here, for conductors we discuss first. See for conductors, for conductors, see for example here, temperature increases, temperature increases na in conductor. For example, this is the conductor. Here see, number of free charges is more is there, number of free charges more is there, means number of electrons per unit volume is more. So when temperature increases, what happen na, it absorbs thermal energy and it will vibration increases, means when temperature increases, vibration of particle increases, vibration increases, vibration increases, what happen here? Collision increases. Collision increases. Collision increases now. What happen here? Collision, more collisions is there. What happen here? Relaxation time. Relaxation time decreases. Relaxation time decreases. For example, see here, what is a rho now here? Rho equal to what? M by Ne square tau average. Resistance now here, M L by Ne square tau A. See here, tau is what here? Denominator is there. Denominator value decreases, definitely resistance increases. See here, for resistivity, denominator, average means relaxation time is denominator is there. Denominator value decreases means numerator total value is increases. So means resistivity also increases. Means when temperature increases, vibration of particle increases. While vibration increases, what happen? Automatically collision increases. Collision increases, relaxation time decreases. When relaxation time decreases, what happen here? Resistance and resistivity both increases. Why? Because average relaxation time is denominator is there. This is the formula for resistivity. What now? M by N is equal to tau average. Tau is where is here? Denominator. So denominator value decreases, automatically numerator value, total value is more is there. That's why it gets, so resistivity increases. Here see resistance, ml by n is equal to tau a. So tau decreases, what happen? Resistivity increases. So that's why here temperature increases. Because of that, what happen here? Resistivity and resistance and resistivity increases. One more case is there here. When temperature increases, what happen now? In conductor, atoms and molecules is there. See whatever here, three bands is there. See, conduction band, energy gap, and valency band is there. Yes na? See, in atoms and molecules, whatever the electrons in the valency band, it get energy when temperature increases. What happen? It jumps to conduction band. Conduction band means what happen here? Number of electrons increases. Means because of ionization. Ionization of electron. Ionization of electron means the process by which ions are formed, either losing the electron or gaining the electron. So because of either losing or gaining of electrons, ions are formed. So what happen here? N value increases. Number of free charges in the conductor increases. So number n value increase now here. N means here, so now number of, see here, number density, number of free electrons per unit volume, it increases. What happen now here? Denominator value increases, numerator value automatically decreases. Means resistivity and resistance both are decreases. Here two cases is there. Here see, for temperature increases, relaxation time decreases. Relaxation, what here? Denominator is there. So denominator value decreases means numerator value increases. So resistance and resistivity increases according to this one, relaxation time. According to ionization of electron, ionization of electron means the process by which ions are formed, either losing or gaining the electrons, either losing or gaining the electrons. So what happened? Number n value increases. N value increases now here. N is denominator is there. N means number of electrons per unit volume. So a number of electrons per unit volume increases because of ionization of energy. Why ionization of energy form now? This, when temperature increases, electrons in the valency band, it will absorb energy and jumps to the conduction band. So that case, what happened? N value increases. When n value increases, resistance and resistivity decreases. Why? Because n is denominator is there. N increases, resistance and resistivity decreases. See here, two cases is there. Which one is dominating? That is the change in, while changing the temperature, that will be we consider. See for example here, for metals, means metals are conductors. For metals, they have they have 10 power 29 electrons per meter cube. 1 meter cube, how many number of electrons in the uh, metals na? 10 power 29 electrons per meter cube at room temperature. At room temperature, yes na? At room temperature, this many is there. So means very high, very high. So increase in n value, increase in n value is insignificant. Insignificant. So insignificant means not consider. Why not consider na? Here see, number of electrons increases because of ionization is, or 10 electrons 20 electrons increases, but here how many is there? 10 power 29 electrons per meter cube. So means comparing with this, it is not dominating. So because of that, so whatever the resistance and resistivity decreases because of ionization of electron, it is not dominating the, when temperature increases relaxation time decreases, that get resistance and resistivity increases. So this one is not to consider. Why? Because it is very less, so comparing with this, so that's why. So it is considered, means when temperature increases, what happen now here? Because of temperature increasing, vibration of electrons increases, automatically collision increases. Collision increases means relaxation time decreases. When relaxation time decreases, resistance and resistivity increases. Because of relaxation time is denominator is there. What is the formula for resistivity? M by n is equal to tau average. Tau is in denominator, it decreases means resistivity increases. For resistance, ml by n is equal to tau a. Here denominator is there, tau. Tau means relaxation time. Denominator decreases means resistance also increases. Because of temperature increasing, resistance and resistivity increases, which is dominating of ionization of electron. Means because of ionization of electron, number n value increases, but it is not considerable, insignificant, means it is not considered. Why? Because comparing with this, it is less change. So that's why it is only we consider. So for conductors, temperature increases, resistance and resistivity increases. Because of this is the reason, ionization of electron. So because of ionization of electron, number density is not more increases, so less only. So it is not dominating this one. So that's why when temperature increases, resistance and resistivity increases, not decreases, but decreases, which dominate this one than this. So that's why it is only we consider. So means when temperature increases, resistance and resistivity increases. Resistance and resistivity increases for conductors. For conductors, so we discuss about uh, semiconductors. So semiconductors means, uh, what are semiconductors now? Silicon and germanium. We can write the second one, semiconductors. Semiconductors. So before this here, see for what is the relation between resistance and resistivity and temperature. For copper, for example, see graph we can draw. See here, it is the resistance or resistivity along y axis. Along x axis we can take temperature. Temperature, yes now see here how it will change now. See temperature increases, resistance and resistivity increases. So that's why this is the graph for copper conductor. See how it is now, it will be increases, this increases. This is the graph for resistance or resistivity versus temperature. Yes na, this one. See for example, for conductors, temperature increases, vibration increases, collision increases, relaxation time decreases. Relaxation time where it is denominator, so automatically resistivity increases. See here for resistance, relaxation time where it is denominator, denominator decreases means resistance increases. That's why temperature increases, resistance and resistivity decreases. But here also number increases, but its number is not more, much more increases, so very less. That's why it is negligible, because of less increase in value comparing with this one. So that's why temperature increases, resistance and resistivity increases. This is the graph between resistance and resistivity versus temperature, how it is na increases. For semiconductor na, for example here see germanium and silicon, these are the semiconductors. For example see, temperature increases, temperature increases, what happen now? Here also same, vibration of particle increases, collision increases, automatically relaxation time decreases, relaxation time decreases, relaxation time decreases. What is resistance? So ml by ne square tau a. So means here tau denominator is there, so means automatically resistance increases, relaxation time increases means denominator value decreases, sorry, relaxation time decreases, resistance increases. Resistivity m by Ne square tau. Here also same, tau is what? Denominator is there. Denominator value decreases means resistivity increases. Resistivity increases. One more condition is there. What that one? Ionization of electron. Ionization of electron. Ionization of electron means the process by which ions are formed, either losing the electron or gaining the electron. For example, see, in this has three cases is there. Here conduction band, valency band, energy gap. In silicon and germanium, energy gap is more there, but in case of conductors it will be overlapped. So how it is now? Both are overlapping, so that's why here electrons easily jumps, but not more, much more comparing with the number of electrons in unit volume. Yes na? Here see, ionization of electron, what happened now here? In this case, what ionization of electron means? The process by which either losing or gaining the electron, what happened? Ions are formed. Ions formed means what happened here? N value increases. Number of electrons per unit volume is increases. Number of electron per unit volume increases means N is denominator. So increases means resistance decreases. Here N denominator increases na, rho value decreases means resistance and resistivity both are decreases, while increasing the N value, number density, number of free charges per unit volume increases, resistance and resistivity decreases. But here see, for semiconductor number of electrons per unit volume is very less. So that's why relaxation time not dominating the ionization of electron. Here see, for semiconductor, after ionization, number density, number of free charges, free electrons per unit volume, for unit volume, what now here? It will increases. Why? Because here holes and electrons both is there, that's why it will be increases. Comparing with relaxation time, it is dominate for conductors, but in case of before temperature increasing, it has less number of electrons, very insignificant, means not more number of electrons. So while temperature increases, N value increases, number of electrons per unit volume increases after increasing the temperature. That's why here resistance and resistivity decreases. It is dominating comparing with this one. So why not? Initially relaxation time very less decreases. Why? Because less number of electrons is there, less number of free charges is there. But after ionization of electron, what happened? N value increases, dominate this relaxation time. So that's why here resistance and resistivity decreases. But here relaxation time dominating the ionization of electron, so means N value. So that's why here resistance and resistivity increases when temperature increases for conductors. But in case of semiconductor, what na? Resistance and resistivity, temperature increases, resistance and resistivity decreases because of number of free electrons per unit volume after increasing temperature dominate, N value dominate than relaxation time. Because of that, resistance and resistivity decreases while temperature increases for semiconductor. It also happen, but it is not dominating this one. It is insignificant. Insignificant. It is significant. It is significant. Here, why it is significant now? N value increases. N value means here holes and electrons both is there. Both is there. That's why N value increases more than relaxation time, decreasing relaxation time. That's why resistance and resistivity decreases for semiconductors when temperature increases. See last one now, here we have what now? For alloys. Before that, here we can draw graph for this one. See what is the graph for this one now? I write here graph. See, it is resistance or resistivity. It is y axis. Now y axis what we can take? Resistance and resistivity. Along x axis what we can take now? Temperature. See here how it is now. See, when temperature increases, resistance and resistivity decreases. Resistance and resistivity decreases. It is the relation between resistance and resistivity and temperature for semiconductor. For conductors, temperature increases, resistance and resistivity also increases because of relaxation time dominating the ionization of electron. So that's why n value increases, but it is not dominating the relaxation time. So that's why resistance resistivity increases there. But here resistance and resistivity decreases because of relaxation time not dominating the ionization of electron, means n value, number of free charges per unit volume. Why? Because here number of free charges per unit volume increases extremely because of holes and electrons. Both are participating in conduction. That's why here n value increases more than relaxation time, decreasing of relaxation time. That's why n value dominate relaxation time in case of semiconductors when temperature increases. That's why temperature increases, resistance and resistivity decreases. This is the graph. See, for alloys we can discuss here. Alloys means what here na? Nichrome, see, manganese and constantan. These are the alloys. For example, nichrome na, here nickel, chromium and iron combination. Manganese na, nickel, copper and manganese. Constant na, nickel and copper only. Yes na? These are the nichrome, means these are alloys. Alloys means two or more metals combined together to form a alloy. Yes na? Two or more metals combined together to form a alloy. So that means nichrome, manganese, constantan. These are the alloys. See, these all are heating elements. What now this one? Heating elements. So what now here? When temperature increases, there is no effect on alloys. So means there is no effect on resistance and resistivity. Resistance and resistivity does not change, do not extremely changes. Yes na? So for that, see, for example here it is a resistance or resistivity on y axis, x axis we can take temperature, x axis we can take temperature. How it is na? Like this only, it will be not extremely, means not affect the resistance and resistivity for alloys. So alloys means here combination of two or more metals. For example, see, nichrome, nickel, chromium, iron, manganese, nickel, copper, manganese, constant in a nickel, copper. Yes, na? See here in this one, here nickel combination is okay, no delay. Here nichrome, nickel, chromium and iron, manganese, nickel, copper, manganese, constant in nickel and copper, nickel and copper. See this one. So this now all are heating elements. So because of heating elements, temperature increases, there is no effect on resistance and resistivity. There is no change in resistance and resistivity. So that is alloys. See once again what here, for conductors temperature increases, vibration increase, collision also increases, automatically relaxation time decreases. So relaxation time decreases. What now here? Relaxation time, where it is in formula, resistance resistivity equal to what? M by N is equal to tau average. Tau denominator is there, so denominator decreases na, numerator increases. Here also same denominator is there, it will increases. So that's why relaxation time decreases, resistance and resistivity increases. When temperature increases, relaxation time decreases. That's why resistance and resistivity increases. For example, ionization of electron, one more case is there we have. So what ionization of electron? According to this, what ionization of electron means the process by which either losing electron or gaining electrons, what happen na, ions are formed. So that ions are formed means n value increases. N value means number of free charges per unit volume, it increases. It increases means resistance and resistivity decreases. Why? Because here denominator is there n value, it increases means this value decreases. But here in case of ionization of electron for conductors, already for metals they have very high number of free charges per unit volume. Yes na? So temperature increases now, what happened now here? There is no, the increase in n value is not dominating the initial values. So that's why it is not dominating, means comparing with this one, what now? It is not dominating. Ionization of electron is not dominating the decreasing relaxation time. So that's why temperature increases, resistance and resistivity increases for conductors. Now for in case of semiconductors, what are semiconductors? Silicon and germanium. For this temperature increases, vibration increases, collision increases, relaxation time decreases. Relaxation time decreases means resistance and resistivity increases. But here for ionization of electron, what number density increases, number of free charges per unit volume increases. Why? Because for semiconductor, initially less number of electrons is there in germanium and silicon. When temperature increases, what happen here? N value increases because of holes and electrons. Number density means number of free charges per unit volume increases extremely comparing with initially. That's why ionization of electron dominate the relaxation, decreasing of relaxation time. So means automatically N value increases comparing with relaxation time, it is more. That's why N increases, resistance and resistivity decreases. It is the graph for resistance and resistivity versus temperature. It is the graph for resistance and resistivity for copper, means conductors, increases here, here decreases. For alloys, now there is no change in resistance and resistivity. It will be maintained constant. Why? Because it are all are heating elements. This is the effect of temperature on resistance and resistivity. Yes, na? So later we will discuss temperature coefficient of resistance. It is the next one. See, I think it is good, is understood all of you. See, next one is coefficient of temperature coefficient of resistance. Here, temperature coefficient of resistance. Temperature coefficient of resistance, na, it is represented by alpha. Coefficient of thermal resistance, we call it as otherwise. See here, for example, experimentally it is proved. Experimentally what now here? See, for example, T, initial temperature is T. What we are doing now here? It's temperature T2, dt increases, dt. So means temperature increases to dt times. What happened? See, resistance increases. For example, see initially resistance R naught. What happened now? It one. So R naught to dr it increases. Understood this point? See, temperature T is there initially. What we are doing now? Its temperature increases d times, dt time. Yes, na? So what happened initially? T temperature now resistance is R naught. T increases, temperature increases, resistance also increases. How much? R plus dr. It also increases. See here, comparing with dr. See here, dr is directly proportional to increase in temperature. Why? Because temperature increases, resistivity increases. See, resistance increases. So that's why we can write. So means here resistance increases, temperature increases, sorry, resistance automatically increases. See here initially T temperature, resistance R naught. What we are doing? T to dt increases. What happened? Resistance also R to R naught to dr increases. Tt temperature increases, dr resistance increases. So that's why we can write dr is directly proportional to dt. Means dt temperature increases, resistance increases dr times. So means here, see this initial value change. What happened now? Dr value also changes. That's why we can write here dr is proportional to initial resistance. Dr is directly proportional to initial, means change in resistance. I write here better. Change in resistance. Change in resistance. We can write what not dr. This dr is change in resistance is directly proportional to change in temperature. Change in resistance is directly proportional to initial resistance. Initial resistance. These two here, see it one we can take one, it we can take two. What we can write take now here? So dr is proportional to R naught into dt. R naught into dt means dr is means change in resistance is directly proportional to initial resistance and change in temperature. Initial resistance and change in temperature. We can remove proportionality now. What we can write here? Dr equal to alpha R naught dt. Alpha R naught dt. This alpha we call it as coefficient of thermal resistance. Coefficient of thermal resistance, or we can write temperature coefficient of resistance. Temperature coefficient of resistance. Here see, We can take now here both side integration. What we get now here, integral dr equal to integral alpha r naught dt. Where to where we are taking starting, what is the temperature, initial temperature Ti, final temperature Tf. Yes na. So initial resistance r naught, final resistance Rf, means Ti to Tf temperature increases, what is resistance where to where increases, Tr to R naught to Rf increases. We can integrate now here, what we get now, Dr means R we get. So what is the interval, R naught to Rf we get. So temperature now here, see alpha is constant, outside we can write here R naught also outside we can write, what, because constant. See here what now here, dt means T we can get where to where, T initial to T final, T initial to T final. So we can write here R final first. Why? Because upper limit first minus lower limit, that equal to what now here, alpha R naught. See here final means upper interval first we can write T final minus T initial. Yes, now this we can get. See here actually change in resistance is directly proportional to change in temperature. Change in resistance is directly proportional to initial resistance. From this we can write change in resistance is directly proportional to initial resistance and change in temperature. So we can remove proportionality, we can add constant, proportionality constant, that is alpha, that we call it as coefficient of thermal resistance or temperature coefficient of resistance. See here, so we can change here this value changes. So where to where, initial temperature to final temperature, initial resistance to final resistance. So that's why we can take for finding, we can take integration both sides. What now, where to where, Ti to R naught, Tf Rf. So we can integrate, what we get here, Dr means R, dt means T we can get. What is the intervals, R naught to Rf, Ti to Tf. First upper interval, lower interval, upper interval, lower interval, alpha R naught, Tf minus Ti. So we can write here Rf equal to this R naught, it changes to that side. So means R naught plus alpha R naught. So Tf minus Ti now we can write Tf minus Ti we can write delta T we can write, means change in temperature. I write here, so means change in temperature. See here Rf means final resistance equal to R naught, here both is there common, we can get 1 plus alpha delta T. It is the formula for final resistance when temperature increases delta T time. What is the final resistance na, R naught into 1 plus alpha delta T. Here R naught means initial resistance, alpha means coefficient of thermal resistance, delta T means change in temperature from initial to final temperature. So this case, from this we can write alpha also. See here, from this here we can write R naught changes to this side, what we get now here, Rf R final minus R naught by here R naught changes now here R naught, see delta T, so equal to alpha, means alpha equal to what we can write now here, final resistance minus initial resistance by initial resistance into change in temperature, that equal to alpha. Or from this again one more we can write, so delta T equal to what we can write now, R final minus R initial by R initial into alpha. This also we can write according to situation. This three formulas we can use, means R final, this is final resistance equal to initial resistance into 1 plus alpha into delta T, or alpha equal to coefficient of thermal resistance. We want to find coefficient of thermal resistance, we can use, this is the formula, alpha equal to what, R final minus R initial by R initial into delta T. Or we want to find out delta T na, what we can write, R final minus R naught by R naught into R alpha. See for example in this case, actually resistance equal to what, rho L by A. Instead of R we can write rho L by A, we can write any change is there not, that we can check. Here you can take now this one, alpha equal to what, R final minus R initial by R initial into delta T. Yes na. See R we can take, otherwise this formula we can take, it is the main formula na, R final equal to R naught into 1 plus alpha delta T. So anyone we can take, it will come. See here R final means what we can write here, rho final L by A, length area not changing. See here rho naught means R naught L by A. So what we get now here, 1 plus alpha delta T. So means here L by A cancel, what we get now here, rho final equal to rho naught into 1 plus alpha delta T. It is the formula for final resistivity equal to initial resistivity into 1 plus alpha d. From this alpha equal to what we can write now here, alpha equal to rho final minus rho initial by rho initial into delta t we can write. It is the formula for coefficient of thermal resistance by using resistivity. What is the formula now? Alpha equal to rho f minus rho naught by rho naught into delta t. So by using resistance na, alpha equal to resistance, final resistance minus initial resistance by initial resistance into change in temperature. Yes na, it is the temperature coefficient of resistance. By using this we can do the problems. See first problem. For example, first problem I write here. See, a wire of um, a wire of an heating resistance of heating element. I write now here. Um, a wire of resistance, a wire of resistance 100 ohms, 100 ohms, or otherwise a heating element of resistance. 1 minute. See what's the problem now here? Resistance of, see, resistance of heating element, heating element, heating element at room temperature, at room temperature 27 degrees, room temperature is 100 ohms. Yes na, at what temperature, at what temperature, at what temperature the resistance of heating element is, resistance of heating element, heating element is 117 ohm. Alpha equal to 1.7 into 10 power minus 4 Celsius minus 1. It is the alpha value. It is the problem. See once again, the resistance of heating element at room temperature is 100 ohm. At what temperature resistance of heating element is 117 ohm? So that we want to find out. See here, we have here resistance of heating element at room temperature. So means initial temperature. What is initial temperature? 27 degrees Celsius. See, at this temperature what is the resistance? R not equal to 100 ohm. See, at what temperature means T final, at what final temperature final resistivity, final resistance is 117 ohms. So means we find they give alpha value also. Alpha equal to what? 1.7 into 10 power minus 4 ohm. It is the, sorry, not ohm, Celsius minus 1. It is the alpha value. So by using these values we find the final temperature. For that what we can use formula is na, so final temperature na we can use this one. See actually here final resistance na Rf equal to R naught into 1 plus alpha delta T we can use. Alpha value we want na final resistance minus initial resistance by initial resistance in delta T. So delta T here this we can use. See here delta T equal to what na here? R final. So R final is what here? 117. I write here formula first. R final minus R initial by R initial into alpha value, alpha. See we can write here R final is 117 minus R initial 100 by R initial na 100 into alpha value 1.7 into 10 power minus 4 Celsius minus 1. See here, 1 minus 100 na, so means 17 by 17 na, here we can write 1.7 into 10 power minus 2 we can write. Why? Because here 2 zeros is there, we can reduce this one, so minus 2. See here, point remove na, here we can write 0 added to the numerator. Yes, now 170 by 17 into 10 power minus 2. See here 17 ones, 17 tens. So means 10 by 10 power minus 2. So means 10 into 10 power plus 2 we can write. Why? Because numerator will change. So what we get now here? See, shall I erase the here? See here, see what we get now here, delta t. Delta t means t final minus t initial equal to 10 into 10 power 2 means 1000 we get. Yes, t final equal to 1000 plus t initial. What is the t initial value? 27. We can write here 1000 plus 27. What we get now here, T final equal to 1027 degrees Celsius. What is the final temperature now? 1027 means at 1027 degrees resistance of heating element is 117. What they give here, resistance of heating element at room temperature is 27 is is 100 ohms. At what temperature resistance of heating element is 117? Then find the, what is we can find out at what temperature, that we can write. What is the initial temperature they give? Room temperature means 27, initial resistance 100, final temperature we want to find. Final resistance they give 117, alpha value they give, just substitution. Yes na, we get what is the temperature na, 1027. See here, next problem, resistance of platinum wire. Platinum wire, I write next problem. See, a resistance of platinum wire. Platinum wire at ice point is 5 ohms, and resistance at, and resistance of platinum wire at ice point is 5 ohms, and steam point is 5.5 ohms. At what temperature, at what temperature resistance of platinum wire is platinum wire is 5.8 ohms, that we want to find out. See here, what they ask now here, see once here, it is the problem, resistance of platinum wire at ice point means 0 degrees Celsius is 5 ohms, and steam point means 100 degrees Celsius. Yes na, what is the resistance? 5.5 ohm. At what temperature resistance of platinum wire is 5.8 ohms? We want to find out first alpha value. By using this and this value we can use and find alpha value. After that, and this we can use find the final temperature. First now alpha value means we can write first what here, ice point. Ice point now here, initial point this one, so what now 0 degrees. Yes, steam point, steam point is final here, so what now here, 100 degrees first case only this one. See this case, what is the resistance? What now here, 5 ohms. This case resistance is 5.5 ohm. By using these values we can find the alpha value. What is the alpha formula? Alpha equal this one, final resistance minus initial by initial resistance into change in temperature. Final resistance 5.5 minus 5 by initial resistance 5 into change in temperature, this one, it is final, it is initial, so means 100 minus 0. Yes na, see we can write here 0.5 by 5 into 100, so means here we can remove point here, added 0 to the denominator, so means here already 100 is there into 10, so means what here, 5 cancel. What is the alpha value now here? 1 by 1000 we can get. What is the alpha value? 1 by 1000 Celsius minus 1. So by using this value we find the, at what temperature resistance is 5.8. What is initial we can take, it is initial, it is final we can take now. So formula what we can find out here, temperature na, so what is at what temperature, delta T equal to, formula we can use this one, so R final minus R initial by R initial into alpha. See here R final means this we can take. Yes na, see delta T equal to, R final means what here, 5.8 minus R initial means this we can use 5 by R initial 5 into 1 by 1000 alpha value. We find out here alpha value. Yes na, see it will changes to numerator means 0.8 into 1000 by 5. So means what we get now here, delta T equal to here 1000 0.8 means 800 by 5 means 5 ones 630 0 means 160. What is the temperature na? 160 degrees Celsius. Why? Because delta T, what na here? Final temperature minus initial. Final initial is what? 0 na. So means T final only we get. T final equal to what we are getting? 160. So means what is the final temperature na? 160 means at what temperature resistance of platinum wire is 5.8 na? 160 degree Celsius. 160 degree Celsius. It is the problems related to coefficient of thermal resistance or temperature coefficient of resistance alpha. Alpha na, this is called temperature coefficient of resistance. For this formula is R final equal to R naught into 1 plus alpha delta T, or we can write alpha equal to what? Rf minus R naught by R naught into delta T, or we can use delta T. Delta T equal to what? Rf minus R naught by R naught into alpha. Instead of R we can write rho na, so rho also rho f minus rho naught by rho naught into delta T alpha. Final means rho final equal to rho naught into 1 plus alpha delta T. It is the relation of mean temperature, effect of temperature on resistance and resistivity. So please, it is very good content for who and all attempting the JEE and NEET. Please see the videos, like the channel and subscribe the channel and share to your friends and relatives. Please subscribe my channel. Thank you.